So today, like I said, the big topic is going to be dilations. We're going to ask the essential question here: how does a dilation transform a figure? So, like, what exactly happens in a dilation? Okay. So, a dilation is a transformation that can change the size of a polygon but leaves the shape unchanged. A dilation has a center. 577. Sorry, page 577. You're actually kind of going backwards some here. Okay. We skipped around a little bit. Just to try out a different order of things. But so anyway, a dilation has a center of dilation and a scale factor, which together determine the position and the size of the image of a figure after the dilation. In fact, if we go back to the warm-up here, some of you guys might be able to tell me. So this was a dilation, therefore, by what we just read there should be a center of dilation. There should be a single point from which we're kind of dilating out from. In this case, I don't want to make a conjecture about what is the center of dilation here. Yeah, Elizabeth. What are the coordinates of it? 0, 0, right. Also called the origin, right? The origin. Yeah, exactly right. The majority of the transformations, the majority of the dilations that we do in the coordinate plane will be centered about the origin. Okay. Just like when we did the rotations, we always kind of rotated about the origin. Here, the center, that was the center of rotation. Here, the center of dilation is generally going to be the origin. When we do some more freehand kind of dilations that are kind of more like this, we'll find a center of dilation in a different way. Okay? So that's right. Does anyone want to take a guess or maybe conjecture about what the scale factor is here? So what's the scale factor? Yeah. Exactly. Where did that come from, Hunter? Yeah, we're taking the 3, the x-coordinates and multiplying by 3, and the y-coordinates and multiplying by 3 as well. We can also see it here in the relationship between the sides, right? The image is 3 times as big as the pre-image. Or in the ratios, too. If you do 9 over 3, image over original, that's kind of like why I was telling you guys we want to start, when we talk about these dilations, we're going to talk about the image length over the original length. That will give us 9 over 3, 3 as our scale factor, or 6 over 2, 3, right, as our scale factor there. So, yeah. So we already kind of looked at those things. Okay. So what we have here then, we're supposed to use triangle ABC and its image, triangle A prime, B prime, C prime, after a dilation to answer the following questions. So we're going to actually kind of take a look here. So right now, if you guys would please, go ahead and do the measures. Okay, please measure to the nearest 1/10 of a centimeter. Go ahead and just measure the sides. I'm going to do the angles for us because the angles are, I don't know, I think there's a little bit more up to interpretation there. So I'll do the angles, y'all do the sides, okay? So I'll do those angles real quick, but you all go ahead and measure the sides. So you're going to do AB, AC, BC, and A prime, B prime, A prime, C prime, B prime, C prime. Again, use the centimeters, please. So to the nearest 1/10 of a centimeter. All right, I'm going to do the angle measures here as best as I can. Hopefully. And then once you get your measurements here, you can copy down my angle measures if you'd like. Oh man, let's see here. 23, 43. It better be like a 7. Alright, well, I'm just gonna. Hopefully that adds up to 180. Okay. All right. So let's see here. Keegan, what'd you get for AB there when you measured it?
6.
6 centimeters exactly? Okay, very good. And then how about AC? What'd you get? Keegan, go ahead, sorry.
4 centimeters.
4. And then what about BC?
3.
3, okay. Cool. And then let's see here. A prime, B prime, Julie, what'd you get? 3, okay. And then what about A prime, C prime there, Julie? 2. And B prime, C prime? 1.5. Aha, okay, very good. So again, we're going to look at, we're considering these two figures here, right? The triangle ABC, and then it was dilated to become triangle A prime, B prime, C prime. And so then we've got these measurements here, so we can see, okay, well, the sides obviously are not going to be equal, but we can kind of tell by looking at the picture. The angles, right, they are equal there, okay? And then we want to come up with these ratios. So this is complete following ratios. So we have A prime, B prime over AB. So let's see here. A prime, B prime we already saw was 3 over AB, which is 6. And then A prime, C prime is 2 over AC, which is 4. And then we have 1.5 over 3. And then drew all these ratios. What do they simplify to be? 1/2 or 0.5, depending on what you want to write in the single box there. But yeah, all are 1/2. Okay. So what do we notice here then about the corresponding sides of the figures? What can we say about the corresponding sides? Are corresponding sides equal? Yeah, no, they're not equal, right? They're not equal. This was 6, this was 3, this was 4, this was 2, that was 3, that was 1.5. So they're not equal. But what can we say about the corresponding sides? They're double. Okay, so like 6 is double 3, 4 is double 2, 3 is double 1.5. Exactly right. They're also all in the same ratio, right? So I'm going to say, that's what I'm going to say. Corresponding sides are proportional. Okay, corresponding sides are proportional. I think that's the key idea here because, again, when we do... Oh, sorry, I know I'm off the screen. There we go. Corresponding sides are proportional. That's kind of like one of the big ideas we've been talking about, right, in similarity, that whole idea of proportion. So we see proportions, we're like, aha, that's important. Okay. And then what about corresponding angles? John, what about corresponding angles is true here? Yeah, corresponding angles are congruent. You got it. Again, we shouldn't be surprised by, right, because we already saw for similar shapes, right, these things look similar, and corresponding angles should be congruent then for similar shapes. Okay. So number 2 then, what similarities are there between reflections, translations, rotations, and dilations? And then what's the difference? So let's talk about similarities. So what are the similarities between reflections, translations, rotations, and then dilations? What are some of the similarities between those 3 transformations with dilations? What's the same about those kind of two groups? If we group together reflection, rotation, translation, and then dilations, what's similar about those 2 groups? How are they the same, or similar, I should say? How are they alike? Yes. Okay, so they're transformations, right? So both are transformation, or both, you know, I guess they're all are transformations. Why are reflections, translations, and rotations kind of grouped together here? What do we call those kind of transformations? Do we remember here? Yeah, Mary? Rigid motion. Rigid transformations. That's right. Whereas dilations, are those rigid motions? Yeah, no, they're not, right? Okay. So that maybe is a difference we'll get to, but I think there's still some more similarities we can say. I mean, yes, they are all transformations. What else? Yeah, Tanner.
They all make like the ratios.
Okay, so the ratios of corresponding sides for both dilations and reflections, translations, rotations would be the same.
Yeah.
So that's true, believe it or not, right? So you might be like, Mr. Whitmire, we never dealt with proportions or ratios of sides for reflections, translations, and rotations. But technically, that's still right. So all the ratios of corresponding sides are proportional. that is a similarity. Okay, there's one more thing here too.
The angles stay the same.
There we go. Corresponding angles are congruent, both in reflections, translations, rotations, and dilations. Corresponding angles are congruent. Okay, so that was similarities. Okay, so what about differences then? What are some differences between those kinds of transformations? Yep.
And they're all different angulations.
Okay, so different motions. Okay, so okay, different motions. I think that's like a good way to say it. Okay. What else is different between reflections, translations, rotations, and dilations? Those rigid motions versus the dilations. What else is going to be different between those sets of transformations? There's one other big one I want to say here. Yeah, Melissa?
So for the reflections, translation, rotations, it remains the same size, so dilation is
There you go. Yes, yes. Size changes in dilations, but not in the others. That's the other big one, I would say. There's actually one other difference we're going to see here in just a little bit about dilations that's more subtle, but it turns out to be true, though. Okay, so size changes in dilations, but not in the others. That's right. That's another big difference, I would say. One thing I did want to go back here about, when you say ratios of corresponding sides are proportional, so dilations, obviously, the ratios could change, right? I mean, here we saw a ratio of like 1/2, but we've seen all sorts of ratios. But what would the ratios of corresponding sides be when it comes to the reflections, the translations, rotations? They'll always be the same number. Yeah, 1. Why is it going to be 1?
Because I think it's congruent, so each side will be the same.
Yeah, the original side will not change when it's then transformed, and so it's just going to be the side divided by the same side, so it's going to give us 1. Exactly right, yeah. Whereas with similarity, we're going to have different ratios and things, so. Okay, cool. Very good. So now we're actually going to do a dilation here. We're going to dilate this line segment and see what happens. Now we're going to do this dilation using some, not as, let's see here, does it say? Yeah, okay. So it doesn't say to use a compass, so we're not going to use a compass here. We're just going to use our handy-dandy rulers. And so it says for A, B, and C here in the steps, I'm actually going to read the original directions. So the dilation of a line segment, the pre-image, right, this original, when we dilate it, it's also going to be a line segment whose length is the product of the scale factor and the length of the pre-image. Okay, so use the following steps to apply a dilation by a factor of 3 with center at the point O to this segment here. I don't know why I put a line there because of a segment, to segment AC. So we're going to dilate segment AC with a center of O by a factor of 3. Okay, so whatever measure AC is, what do we expect the length of A prime C prime to be? So if AC turns out to be like 2 centimeters, we would expect A prime C prime to be what length? 6. How'd you get 6, Elizabeth?
Wait, what was the number before that?
So it was at 2.
Then you multiply that through.
And how did you know to multiply by 3? Yeah, the dilation is by a factor of 3, so it's going to get 3 times bigger, we would expect, right? So let's actually do it. So here's how we're going to do that, all right? Parts A, B, and C all tell us to draw rays. We're going to draw 3 different rays. They all are going to start at point O, but they're going to go through A, then a ray from O through B, and then a ray from O through C. So just go ahead and draw 3 rays. Okay, and and by the way, I would recommend trying this page out because it's going to be a hassle to try and do this. Your rulers don't curve with the page and stuff, so. But don't lose that page because we are going to come back, but for now, feel free to just tear it out. Okay. Okay. So we got some rays going. OA, OB, OC. Okay. we're going to use our rulers then, once you got those rays OA, OB, and OC drawn, we're going to use our ruler to then measure, for example, the length from O to A. So I'm going to turn my paper here to kind of help me with this, and we're going to figure out this distance. So if I look from O to A, so you can see it's not exactly 1 centimeter, but I think it's close enough. I'm going to go ahead and call that 1 centimeter. Okay, so from O to A is 1 centimeter. And now for me to locate A prime, how far do I need to go out from point O? From O to A is 1 centimeter. I want to dilate by a scale factor of 3. So I want to go out 3 centimeters from O. Exactly right. So it's not 3 centimeters from A. Be careful. It's 3 centimeters back from that center. A is 1 centimeter away, so we want to go then 3 centimeters away for A prime. 3 centimeters away from the center of dilation. So again, put your ruler down there and go out 3 centimeters. So something like that. Okay. Okay, and that'll be A prime. Okay, so there's A prime. And then let's do the same thing for B. So let's see here. So from O to B, I'm going to say that's like 0.9. And so let's see here. 3 times 0.9 is going to be what? Yeah.
2.8.
Yeah, 2.7. That's right. So we're going to go out 2.7. That's right. And then let's see here, at O to C is like 1.4. So 3 times 1.4 is 4.2. Yep, 4.2. So we're going to go out 4.2 then from O along C. Like so. And then, so that was B prime, that is C prime. So that's 0.9, 2.7, and then okay. And so hopefully we end up with something like this where all 3 points lie on the same line. Okay? There that all 3 of them are. Okay. Now part E says to measure segment AB, segment AC, segment BC, all that stuff. I'm not going to worry about that. Let's just do the full length. Let's just do AC, the full length here. So AC, it has a length of it's kind of between 1.6 and 1.7. So I'm going to go ahead and call that 1.7. Okay, so AC has a length of 1.7. So if we do 1.7 times 3, like Elizabeth told us to do, we should end up with 5.1. So we predict here A prime C prime should be like 5.1 centimeters if we did our dilation well. And sure enough, there it is. There's 5, and there's 5.1 right there. Okay. So it is. It works out. Okay. A prime C prime is 5.1 centimeters. So it's 3 times as long. Okay. Now, the segment's 3 times as long as the original segment. Does anyone see another relationship that's maybe true about AC and its image, A prime, C prime, after this dilation? Besides the image being 3 times as long, do you see another relationship here between AC and its image, A prime, C prime? Yeah, Shannon, what do you say? It looks like they're parallel. And in fact, they will be parallel. Exactly right. So if you take a line or a segment, and then you dilate it, okay, you will end up with a segment or a line that is parallel to that line as well. Yep, exactly right. So it maintains the slope. The slope will stay the same here, right? The slope of AC is going to be the same as the slope of A prime, C prime. So that's helpful to see that as well. Very good. Okay. All right, so number 3, and this might be a little bit strange here. We'll give it a shot. I think we can do it, right? So make a conjecture about the length of the image of a 4 centimeter segment. So our original segment is 4 centimeters. We want to then come up with the length of the image if it's being dilated with a scale factor of K. So how can we figure that out? If our original segment had a length of 4 centimeters, how can we then use that scale factor of K to come up with what the new length would be? I'm going to pick someone here. So Maria, what do you think? If I start out with a segment that is 4 centimeters long, and then I dilate it by a scale factor of K, what's the new length of that segment going to be? Or what would be an expression for that new length of that segment? Yeah, exactly right, 4K. Yeah, 4K is the image's length. Exactly right. Now the next question here, can the image ever be shorter than the pre-image? And what do you think about that, Maria? And if you want to pass it, that's fine, I can go on someone else. But do you think, can the image ever be shorter than the pre-image? So can your like you have your original, and then your image is like shorter in length than the original. Can that happen? Yeah, it can, absolutely, yes. Yeah, so the image can be shorter than the pre-image. Does anyone have an idea about how we can do that? How can we make the image shorter than the pre-image? Yeah, Mary?
You have a scale factor of refraction.
There we go. Darn it. All right, yeah, that's right. Yep, exactly right. It's got to be less than 1 but greater than 0. So can you give me an example?
Like 1/2.
1/2, exactly right. Great example. A scale factor of 1/2 would shrink our original image. That's right. But it's got to be between 0 and 1, right? Because I was going to say, like, well, what about 5/4? Would 5/4 shrink it? The answer is no, right? It's bigger than 1, so it actually makes it a little bit bigger. So, okay. Let's see here. What can you say about the image of a segment under dilation? Does your answer depend on the location of the segment? Okay, so I do want to point out one thing here. What if our center of dilation, so here our center of dilation was O, and it was, we were dilating ABC. What if our center of dilation here was like B? What would happen then to our dilation in that case? If B was our center of dilation, so if we were dilating AC still, but we are dilating from a point on AC, would our segment, would it move? So if my center of dilation was point B, and I was going to dilate this segment AC, would the segment move like it did here? Like here when it was O, we dilated this and it got bigger, but it moved down here some. Would the segment move? Yeah, Hunter.
No.
Yeah, it would not move, but would it be the same segment though?
No, because AC possibly will.
Yeah, it depends on what the scale factor is, but it would shrink or grow, but yes, it would still be on. It wouldn't have moved like up or down or anything like that. It'd still be in the same position, just longer or shorter or something like that. Don't worry about writing that down though. I feel like that's too much to write down. So okay, moving on. So here, bless you, are some properties of dilations, which maybe aren't as obvious as you might think. So dilations preserve angle measure. You're like, duh, congruent angles, right? Ooh, I forgot here. I should want to hit these vocab words. Sorry. So the center of dilation is the fixed point about which all of the points are transformed by a dilation. Okay. The ratio of the lengths of corresponding sides in the image and the pre-image is called the scale factor. So to sum that up, the scale factor is the image over the pre-image. Okay, you always take one of the sides of the image and put it over the corresponding side of the pre-image. That is the scale factor. Okay, it must be that way. All right. So again, dilations preserve angle measure. Duh. Corresponding angles are congruent. Dilations preserve betweenness. So for example, if you have a point between 2 points and you dilate that shape, then that point will still be between the 2 points of the dilation. Dilations preserve collinearity. What does it mean to be collinear? What does it mean to be collinear? What does it mean to be collinear here? Co means to share, right? Linear means line. So collinear would mean what then, Julia? So again, co means to share. Linear means align, right? So share, align. So if points are collinear, that means they are on the same line. Yeah, that's it. Yep. Points are on the same line. So if you have, if you dilate something, okay, and if points are on a line together, and you dilate that line, the point should still be on that line in the dilation in the image. Here's a really important thing: dilations preserve orientation. Okay, do rotations preserve orientation? They don't, do they? So this is something that dilations do that rotations do not do. Do reflections preserve orientation? No, they do not, okay? So, do translations preserve orientation? Yes, they do. Translations still preserve orientation, but rotations and reflections do not, okay? So, if we see something that's orientation is not preserved, then it is not a dilation, okay? Dilations map a line segment to another line segment whose length is the product of the scale factor and the length of the pre-image. It's like, okay, that's what we just saw earlier there, okay? And then the last one, dilations map a line not passing through the center of dilation to a parallel line, that's what Shannon pointed out, and leave a line passing through the center unchanged. So if you have a line and it's the center of dilation is on that line, the line won't change at all because it's a line. It goes on forever anyway. So, all right, example 1. Not a dilation. What is this transformation we see here in example 1a? A reflection. That's exactly right, Maria. Very good. Okay, that is a reflection. So it's not a dilation. The orientation changes. Okay, here A is in the upper left, but here it's D prime for the image is in the upper left there. So it's not the same orientation. They're different kind of orders. Okay. All right, let's look at B though. So let's see here. All right, let's see here. So Stephanie, for example, does it look like this transformation of ABC to A prime, B prime, C prime, does it look like it preserves angle measure? Yeah, I think so too. I mean, I know that's harder to see. We could maybe measure with our protractors and stuff, but we'll eyeball it there and say yes, that's true. And then between this, again, that's kind of hard to see here because there's not really other points. It's just the vertices. But okay, we'll go ahead and say yes. Does it look like it preserves collinearity? Again, yes. There's not really like points listed there, so we'll just assume that those points that are in between A and B will stay between A prime and B prime in the image. Does it preserve orientation here? Mary, what do you say? Does this transformation preserve orientation?
Yes.
Yes, it does. Yeah, it does. Okay. What's the scale factor here? What is the scale factor here? Okay, so Hunter thinks he's got an answer. Anyone else want to give it a shot? I know, I thank you guys. I just want to see if anyone else wants to give it a shot? All right, Hunter, what do you say it is? 2. Elizabeth, what do you say it is? 2. You said 2? Okay, so Hunter, how'd you get 2?
Because I just saw point A and it's -2, -2, and A prime is -4, -4, and -2 times -2 is -4.
Aha, right. So we take A, which has coordinates -2, -2. A prime becomes -4, -4. So the scale factor then, we had to multiply that by 2. So yeah, the scale factor is going to be 2 there. That's right. It is 2. Alternatively, we could have measured one of these sides, but the problem with measuring one of the sides is that they're not, they're all diagonal, so they're not nice and straight. We'd have to use like the distance formula. Although, we can kind of use the slopes to help us here. For example, to go from A to B, what would that slope be? What would the slope be from A to B? What would the way we have to move kind of be there? So we have to go up from A to B. It looks like we have to go up, 1 maybe? And then right, 1, 2, 3 to get to B, right? Up 1, right 3. Now then from A prime to B prime, how many times do I have to do that? Up 1, right 3, that's 1 time. Up 1, right 3, that's 2 times. So whereas I could go from A to B once going up 1, right 3, I had to go to A prime, B prime twice, 2 of those up 1, right 3s. So that kind of gives you a hint there at the scale factor being 2 as well. I had to use only 1 application of the slope. Here I had to use 2 applications of the slope. That gets tricky when you're talking about like fractions, scale factors, and stuff like that. But for the nice whole number scale factors, it works out really nice. Okay. So, is this transformation a dilation? Mason?
Yes.
Yes. He's right. Mason's like, I knew that 5 minutes ago. I'm stupid. That's okay. Thank you, Mason, for humoring me. Okay. So, go ahead. Take a look at 5 and 6. Try those right now. Give them a shot. I'll give you a few minutes there. Remember, if just one of those properties fails, the whole thing is not a dilation. Okay? So, for example, if orientation, or if like betweenness of points fails, the whole thing's not a dilation. Okay? And be careful, guys. At number 5, those well, I mean, I guess it looks like they're counting by 2s, but their blocks are really counting by 1s. I mean, it's every other number there that's being listed. So anyway, yeah. Anyway. Okay, yeah, one more minute here. If you determine it's a dilation, go ahead and try to find the scale factor as well. Okay? Try to find the scale factor. Once you determine that you think it's a dilation, if one of them is a dilation, try to find that scale factor. There's a couple different ways to do it. Crooked. Oh well. All right, so let's see here. So, Adam, what do you say about number 5 there? Is it, do we have a dilation in this picture, I guess, in this graph?
Yes.
Okay, yes. Were you able to figure out what the scale factor was?
Yes.
2? Okay, so how'd you get 2?
Well, I just looked at all of the pre-image
points,
Uh-huh.
and then I found out the similarity between that and the image.
Okay, so for example, you looked at like point D maybe?
Yeah.
All right, so D has coordinates -2, -2. And so if our scale factor is 2, what would we expect the D prime to be?
Oh man, I just looked at that. That's not right.
Right, it would, so it wouldn't be, but we can still figure it out, right? So what is D prime, what are the coordinates of D prime, or what is the coordinate of D prime?
D prime is -3, -3.
Right, so then the question is, right, what do we multiply? We have D with coordinates -2, -2, and we want to find D prime that has coordinates -3, -3. So the question is, -2 times what gives us -3? Well, the good news is, right, what do we normally use for a number we don't know? X. Now, if I want to know what X is, I can solve this very simple equation, right? So I divide both sides by -2. So 3/2 is the scale factor there. 3/2 is the scale factor, yes. So 1.5 or 3/2. Okay. Did anyone do that a different way besides using the coordinates of points to find the scale factor? Anyone tried a different way besides using the coordinates of the points? Or can anyone think of a different way to do it besides using coordinates of points to do it? Yeah? Hunter, what do you say?
Or you can do lines.
Yeah, you could do some of the lines here because we have some nice like horizontal lines. Okay, or right here, for example. So, I mean, here, for example, CD is a 2, and C prime D prime is a length of 3. So again, image 3 over original 2, 3/2. There it is, right there too. You could use a side. Okay, good. Exactly right. So it's up to you, whichever one you want to use there. And then Evan, number 6. What do you say?
I said no.
No. Okay. Why not?
Because the one side, AB is exactly the same as A.
Okay, right. And then, so that's true. And then what else? So what else would have to be true then? If AB is the same length as A prime, B prime, what would have to be true about the other sides?
They would be the same as
As their corresponding parts. So yeah, so your logic was right. Just make sure you finish off that last piece, because again, it's actually okay that AB is the same length as A prime, B prime, as long as B prime, C prime is the same length as BC, and A prime, C prime is the same length as AC. But that's not the case here. Did anyone see a different way that this thing failed besides the lengths of the sides? Yeah, Drew, what do you say?
I said change orientation.
Changed orientation. Is that what you're going to say too, Melissa? Or did you have a different one? Yeah, changed orientation. There's actually something else you can see here too. What about the angles? Is angle C going to be the same angle as angle C prime? It's probably harder to see, but I don't think it will be, right? And A will probably not be the same as A prime as well. So, but I think the orientation one's much easier to see because it's like, duh, right there, right? Okay. Last little thing I want to look at, and then I'll get you guys some time to work on your homework. This should be real quick, I think. Anyway, determining the center and scale of a dilation. So when you have a figure and its image after a dilation, you can find the center of dilation, and this is really simple, by drawing lines that connect the corresponding vertices. So for example here, if we started with A prime, B prime, C prime, and ABC, to find the center of dilation, you just draw BB prime and CC prime and AA prime. And they all intersect at their center of dilation. How cool is that, right? Very easy. So where they intersect, that's the center of dilation. Okay, now to find the actual scale factor is different. So you'll look here at what they did let's see here, to find the scale factor, it says. So they took, for example, OA, they measured from the center of dilation to the image, 25 millimeters they said, and then they measured from O to B, from O to A right there, 25 millimeters, not the image, they measured to the original. And then O to B was 13, O to C was 19, and they measured to the images as well, so O to A prime, O to B prime, O to C prime. And then they took the image measurements and put them over top of the original measurement, so 50 over 25, 2 to 1, 26 over 13, 2 to 1, 38 over 19, also 2 to 1. Okay, so there's that scale factor. They also could have measured, though, like B prime, C prime, and put it on top of BC, or A prime, C prime, and put it on AC, or A prime, B prime, and put it on top of AB. Any of those would have worked as well. Okay. So we're going to skip letter B there because that's a lot of measuring, but we're going to jump to letter number 8 and do that one real quick. So here the center of dilation is already found for us, so I don't know why it says to determine the center of dilation because it's already there, okay? But we are going to measure OA prime, let's see here. Whoops. It says to use centimeters, but doggone it, that was like exactly an inch it looked like. Alright, so OA prime, ooh. I'm going to say like maybe 2.6, we'll say. And then OA, measure that one here real quick. OA, I see like, 6 times. No. Oh, man. So I think I see like 7.7, but I think it should be like 7.8. Just because I'm looking at the, it'll make the numbers work out nicely. So I'm going to go ahead and say that's 7.8 centimeters. Because it'll make the numbers work out nicely if we say that. Okay. Once again, notice we're measuring from the center of dilation to our image, from the center of dilation to our original point. Okay, so none of this business between that. We're not going to measure A prime A. It's from O to A prime and from O to A. All right, and so if we do that, 2.6 divided by 7.8, 1/3. Okay, gives us that fraction there, 0.3333 or 1/3 as a fraction. Okay, and again, you don't have to do O to A prime or O to A. You could do like A prime C prime over AC, C prime B prime over B CB, A prime B prime over AB. Okay, so all those are options there. Okay, yeah, I think those are all pretty straightforward, so we won't worry about those. So let's get into the assignment then. Okay, I'm gonna give you guys that real quick so you can get started on it.